Hello everyone, welcome to Cracking Vectors Part 4, and today we will be continuing with the formulas that we learned in our last video. So without further ado, let's get started. At the very beginning today, we will learn how to show that a line lies on a plane. Now, while this might seem a bit complicated, it's not. It's actually one of the simplest things ever. I would suggest stick to the first method, or you can go for the second method, which is a bit lengthier, a bit more complicated. So I would suggest you don't. So over here, what you can see is that I will be explaining it with the help of a sum. So over here, we have the equation of a line, as you can see, which is I minus j plus 8k plus 2i minus k into t, which lies in the plane, and then we have the equation of the plane too. So how do we go forward with it? So the first method is that you separate the x, y and z coordinates of the line. So what happens is that once you have separated those x, y and z components, you insert it into the equation of the plane that's given. At times what happens is, instead of giving the Cartesian equation, they might have given you the form where the plane is written in this format. So the plane equals to the position vector plus a direction vector plus another direction vector. So in that case, you would have to do some calculations and then find the direction vector of the normal and then bring it back to the Cartesian form, and then proceed with the method same as below. So once you have segregated the different x, y, z variables, you will plug it back into the equation of the plane. What you will see is that if the line lies on the plane, the t variables will cancel out. When you're simplifying it, it cancels out and you will receive with the same value as the constant. So as you can see over here, you have this constant 12, right? So once you simplify this part, you will be left with 12. Now, if it was not 12, what would happen? If it was not 12, it would obviously not lie on the plane, right? But there are few more subtleties to it. So for example, instead of 12, if the variables still cancelled out, the t variable still cancelled out, and you receive the number 8, for example, instead of 12. What would that mean? It means that this plane that we're talking about, this line and this plane. So if this is the plane, and if this equals to 8 over here, this means that the line goes like this. So it is parallel to the plane, but it is not contained within the plane. Okay? If you see that the t variable does not cancel out, right? If you find something like t equals to 12 or 2t minus 3 equals to 12, from where you can simplify and find a value of t, which in this case will be 7.5. So in that case, what would that mean? That in that case, it would mean that if this is the plane, then the line is intersecting the plane. Okay, so that is all the variations of it. So over here you learned how to show that a line lies on a plane. If you're asked to find the coordinates of a line which is intersecting the plane, then you do the same thing. So you just separate the x, y and z variables, and then you plug it back in to the equation of the plane, and then you find the value of t. Now this t value that you found over here, if you plug this in back into the equation of the line, you will get the position vector of the point of intersection of the line and the plane. I hope that is clear to all of you. Moving on to method number 2, not my favorite, but since it is in the course book, we should all be familiar with it. So in method 2, what we do is we substitute variables of t, right? So if we for example consider t is equals to 0, If we, for example, it's something like a trial and error method kind of thing where every time the answer needs to match with 12 at the end to make sure that it lies on the plane. So we just check with two variables and that's enough. I have not seen enough use of it in the mark scheme, so I would ask you guys to avoid it. So they have taken t is equals to 0 and then t is equals to 0 in this equation, and then they find a value of r, right? Which now will be r equals to 1 minus j plus 8k, and then this equation they substituted back into the plane. So you have x equals to 1, y is equals to minus 1, and z equals to 8 over here. And when they substituted it into the planes equation, they got 12. Again, if you substitute t is equals to 1, they will end up with 12 again. Since it's always coming up to 12, this shows that it lies on the plane. Okay, moving on to our seventh formula, or the seventh calculations that we need to know, which is how to find the foot of perpendicular from a point to a plane, which you will learn in the next method. So I have just included it in the second method. It is just for you at this point of time to know that you need to know how to calculate it. So let's move on. So how to find the shortest or the perpendicular distance between a point and a plane. So now if they only ask for the shortest distance, you will obviously go with the first formula over here, because it's very short, precise and concise. However, if they ask you to find the foot of the perpendicular from a point to a plane, you need to do method 2 and then you need to find the foot of the perpendicular. So let's get started. So what is method 1? In method 1, we see that let the point be P and let Q be any point on the plane. It can be any point at all. So the shortest distance will obviously be PQ, which is OQ minus OP. And then the distance will be the value you got of PQ, which is with the dot product of the normal. Then you have to find the modulus of that dot product divided by the modulus of the normal. Then moving on to method number 2, here let the point be P and the foot of the perpendicular be F and the normal of the plane be N. So then what happens is OF is equals to OP plus TN. So what is T? It is just a variable. We will multiply with the normal. So N is the direction vector of the normal. So why do we do it? Just like in equations of the line, where since you do not know how far along the line the point is, you need to multiply with a scalar constant with the direction vector. Similarly, with the direction vector of the normal, you need to do the same. So now what you do is you substitute the parametric equations of OF in the Cartesian equation of the plane to obtain the value of t. So what do we mean by here? So just like here, what we did is we were plugging back the variables. Just like over here, we were plugging back the variables. You need to plug back these variables again. So in this case, for example, this is so you need to plug back the variables of OF, right? So let's say this is OF and you have this parametric equation for OF where the variables are separated, and then you plug this back into the equation of the plane and you will get what there is to find. Moving on to our moving on. So that is how you will find the value of t. Now, if you substitute the value of t in the equation of OF, you get the position vector of f, obviously. And then you just need to find the distance PF. So you know the position vector of P, you know the position vector of F. You can easily find PF using our very first formula that we learned yesterday, right? Or the last video. So here we can try out a sum. I would ask all of you guys to pause the video and try out the sum over here. Find the perpendicular distance from the point A. We are given the points, coordinates to a plane whose Cartesian equation is given by, and then we have the value. So pause the video and try it out, everyone, please. So by now, I hope that you guys have solved it. So let's go forward to the explanation. It's okay if you haven't. You will learn it in just a few minutes. So here we have the point A. We have the Cartesian equation of the plane, and one other point that we did know from the plane is that the point Q lies on the plane. So what is the point Q? The point Q is 0, 0, 2. So this is a point which can be given, or this is a point that you can find by substituting 0 in any two of the other x or y or z variables. It doesn't matter. So then what you find is, you find AQ. So AQ will be OQ minus OA, obviously. So you will find AQ. Then the perpendicular distance from A to the plane will be AQ with the dot product of the normal. So the unit vector of the normal, right? So then you have A, you're doing the dot product, and then you have the direction vector, and then you need to divide it with the magnitude of the direction vector to find the unit vector of the direction vector. So what you're left with, 1 by root over 3 units. So that is one way you could find the perpendicular distance. The second way is, so the method 1 was the method 1 described over here, right? So we are following this. And then you have method 2, where let n be the foot of the perpendicular from A to plane 1. So the plane will be 1, 2, 2 plus lambda 1 minus 1, 1. And then if you substitute 1 into the equation of plane 1, what you're left with is 1 plus lambda 2 minus lambda dot 2 plus lambda with the dot product of 1 minus 1, 1 equals to 2. So now you might be asking, how did we get this? How do we get this? So for the foot of the perpendicular, obviously the foot of the perpendicular needs to pass through this point, right? For the perpendicular distance, we know that for the perpendicular distance, it needs to be at a right angle. And any line which is at right angle to the plane is the normal. So the equation of this line, you have the point A on this line. So you have A, and then you can find the direction vector or the equation of line for this line. So this will be the position vector plus the normal into lambda. We always multiply it with a scalar constant. So if you separate the x coordinates, y coordinates, and z coordinates, you receive this. Now, doing the dot product with the normal, you will receive what? You will receive 2, because what you're essentially doing over here is plugging it back into the equation, and it needs to fall in the plane, right? So doing the dot product gives you 2. In this way, you can find the value of lambda. Now what you will do is, once you have the value of lambda, you can plug it back into, once you have the value of lambda, you will use this equation again to find ON, which is the foot of the perpendicular. So once you find the foot of the perpendicular, so you found N, you already know A, you found N. So simply you need to find the equation of a line connecting these two variables, and this will give you the equation of the perpendicular line, right? And then the shortest distance will obviously be the magnitude of that. So you have the direction vector, and then finding the magnitude of that gives you 1 by root 3 units. And as you can see, the answer matches in both methods. It got a bit messy, so we will try to make it more neat from now on. But you all, I hope, understood where to plug in which variable. Okay, so now moving on to our next part, which is the shortest or the perpendicular distance between a line and a plane. So, to find the perpendicular distance between a line and a plane, let's say you have the line PQ, right? And then you have the equation of the plane. So, from the equation of the plane, you can find the normal. Or if the plane's equation is given in the Cartesian form, you already know the normal. So very simply, let Q be any point on the line and P be a point on the plane. So in the equation of the line, you already have the position vector of 1 point, which is this point, right? So consider that to be Q, simple, and then you can consider a point P which is on the plane, find that point out. If the equation of the plane is given in this form, so plane is equals to position vector of 1 point plus the direction vector of a line on the plane plus the direction vector of another point on the plane. So here you have another position vector, right? Use that as P. This will be your P. This is your Q. And then from P and Q, you can find PQ. So PQ will be OQ minus OP. And from there, you can find, just plug it back into this formula. If you plug it back into this formula, you can easily find the distance. If you want a video on the derivations of these formulas, do let me know and I will cover that for you too. But for now, we're just focusing on how to do the sums. Once you found out all the different ways to approach a sum and have all those concepts clear, then we can move on to the further concepts or the further in-depth knowledge on how the formulas came to be. So now we have the shortest or the perpendicular distance of plane from the origin. So for the shortest the perpendicular distance of plane from the origin, we again have a formula. Make sure this is a formula you know very clearly because this has been coming a lot in the recent years. In 2022, 2021, I saw this come quite a few times in the 9231 papers. However, this formula is not given in the course book. Not given in course book. And I have not found this formula in other books too. So make sure you learn it. Okay. So over here what we will do is you have the equation of the plane and you just need to find the distance from the origin. So x is our variable, y is our variable, z is our variable, and a, b, c are the constants or the coefficients, right? So simply plug it back into the formula where the distance is d divided by a square plus b square plus c square. So we can see this very simple sum for it. So you need to find the perpendicular distance of O from the plane. So the distance will be 8. So the distance can never be negative, right? So you can just not consider this 8. It doesn't mean it's not minus 8. It is minus 8, but you can just not consider the minus over here. Just consider 8 because distance can never be negative. And then you have the distance. Now, for the angle between the two lines, this is something you should have learned in the P3 syllabus of vectors. So the angle is given by cos alpha is equals to the dot product of the direction vector of line 1 and line 2 divided by the magnitude of those direction vectors, and then you will find the angle. How to find the angle between a line and a plane? So between two lines it was easy, but between a line and a plane it gets a bit more complicated. So over here, but not too complicated, so don't worry. You have the angle between the line r is equals to a plus bt and the plane with normal n. So over here n is and b are representing the direction vectors of the normal and the line respectively. So cos alpha will be, again see, there is a very big similarity and an easy way to method remember this formula. So in this formula and in this formula, what are we doing? Simply dot product of the direction vectors divided by magnitude of those direction vectors Okay, so then you can find the formula, find the value. Now, depending on the size of alpha, the acute angle between the line and the plane is either. So cos alpha can either be positive or negative. So if you find the negative value, obviously it's a obtuse angle. If you find a positive value, it's an acute angle. So in some questions it is specified, in most questions actually, it is specified to find the acute angle. So in that case, what you will do is you have the obtuse angle, and then you will subtract 90 from it, and then you will find the acute angle. And if the value is already positive, the cos alpha value is already positive, what you just need to do is theta will be 90 minus alpha. Okay, so if cos theta is already positive, the value you will get for alpha, you need to subtract it from 90 to find the angle. So most students, what they do is they forget to do this final step, but this is very important. So make sure you do not forget to do this modification. So now we will move on to a sum. Here you're asked to find the angle between the line 8i minus 3j plus k, and then you have the direction vector of the line, and the plane, you have the Cartesian equation of the plane. Very easy, just follow the formula. So pause the video, solve the sum. I hope by now you are done with solving the sum, so let's move on to the solution. So what you can see here is they have directly inputted into the formula. You could find the dot product separately and then input it. So doing the dot product, I can show you the entire sum in case you want a revision on how to find the dot product, right? So over here, we're finding the dot product of the direction vectors. So we're finding the dot product of the direction vectors 8 minus 3 and 1 with the direction vector of the normal, which is 3 minus 1 and 0. So for the dot product, it is very simple. All you do is you need to do the dot product of the direction vectors, right? So it is 2 minus 1. I saw the equation wrong, and you have over here 3 minus 1 and 0. So simply you multiply this with this, and then you add the multiplication of this with this. So 2 into 3 is 6. Then add the multiplication of this with this. So that is minus 2. add the multiplication of this with this, so that is plus 0. What you're left with is 4. And then you just insert the value over here, so you can see that it is 4. And then once they have found the value of cos alpha over here, they got a positive value, right? So they got 65.06 degrees for alpha. Hence